Hello everyone and welcome back. In this video we will talk about hypothesis testing and the components of a hypothesis test in detail. Now, hypothesis testing is typically used when we want to determine whether a population parameter has changed from the past, and it enables us to make a decision between two competing claims which are called hypotheses. Hypotheses are models that we adopt temporarily until we can test them once we have the collected data. The null hypothesis is the claim being assessed in a hypothesis test and is denoted by H0. It is generally the hypothesis of no change or no effect, and we typically write the statement where the population parameter, we'll call it x, is equal to some specified value, which we'll call x0. We will assume that the null hypothesis is true until we obtain evidence to suggest that it is false. And the alternative hypothesis proposes what we should conclude if we find that the null hypothesis is not plausible and is denoted by HA, or sometimes you'll see H1. You can think of the alternative hypothesis as the opposite claim to the null hypothesis, and it can take on one of three forms. It can either be x does not equal x0, or x is greater than x0, or x is less than x0. So how do we choose the hypotheses? Well, the appropriate hypothesis arises from the context of the problem. We will identify a parameter and then choose a null value that relates to the question at hand. Now, since this chapter is on categorical data, we will focus on proportions. And so we'll write a few examples for hypotheses that deals with the population proportion. For a hypothesis test, the null hypothesis is that the population proportion is equal to some specified value, which we'll call P0. Then the alternative hypothesis can either be a two-sided or a one-sided alternative. So a two-sided alternative is the alternative hypothesis where P does not equal P0. This is also referred to as a two-tailed test. And for a one-sided alternative hypothesis, this is where the alternative hypothesis is either P is less than P0, which is a lower tailed test, or P is greater than P0, which is an upper tailed test. Now let's consider some scenarios, and we'll write the appropriate hypotheses for each one. What we want to test will typically be given as the alternative hypothesis. So let's suppose I wish to test if a coin is unfair. And so we'll let P represent the proportion of heads. So what are the hypotheses for this test? Well, if the coin is fair, this would mean that the population proportion, P, would be equal to 0.5. So there's a 50-50 chance to see heads and tails. And since we want to test whether the coin is unfair, then the alternative hypothesis would be that P would not equal 0.5. So the alternative should be that P does not equal 0.5, and this is the statement where the coin is unfair. Now, the null hypothesis is where the coin is fair. So it is the opposite claim to the alternative, which would mean that P is equal to 0.5. So now let's test if a coin is biased towards heads. So if P is still the proportion of heads, then the coin is biased towards heads if P is greater than 0.5. And so the alternative hypothesis would be that P is greater than 0.5. So this is the statement where the coin is biased towards heads. So this means that the null hypothesis is where P is equal to 0.5. So this is the statement where the coin is fair. Now in some texts, you might see that the alternative is P is less than or equal to 0.5. However, when we are performing a hypothesis test, we can only choose one value for the null hypothesis at any given time. And so we choose the equality instead of the inequality. So now let's suppose that I wish to test if more than 5% of students fall asleep during class. And so if P represents the proportion of students that fall asleep during class, then this means that the alternative hypothesis is that P is greater than 0.05. So this is the statement where more than 5% of students fall asleep. And for the null hypothesis, this means that P is equal to 0.05. And now let's suppose I wish to test if less than 60% of students like vanilla ice cream. So P represents the proportion of students that like vanilla ice cream. Then the alternative hypothesis is that P is less than 0.6. So this is the statement that less than 60% like vanilla ice cream. And this means that the null hypothesis is that P is equal to 0.6. So after we have determined the hypotheses for the test, we will go out and collect the data. Then once we have our data, we can calculate what is called a test statistic, which measures the number of standard deviations away the sample estimate is from the hypothesized value in the null hypothesis. The next step is to calculate what is called a p-value, which is the probability of observing our test statistic, or more extreme than the observed test statistic, assuming that the null hypothesis is true. Now this definition can seem quite confusing at first, but we'll explain this in more detail and how they are used to make our final conclusion. Now a p-value is a conditional probability. It tells us the probability of obtaining results at least as unusual as the observed statistic, given that the null hypothesis is true. And it is used to measure the strength of our evidence against the null hypothesis. So if we have a small p-value, then this means that the result that we have observed is unlikely to occur if the null hypothesis were actually true. And so this means that our data provides sufficient evidence to reject the null hypothesis in favor of the alternative hypothesis. And if we have a large p-value, then this means that the result we observed isn't surprising. And this means that the results are in line with our assumption that the null hypothesis will model the world and we have no reason to reject it. And so we will often say that we fail to reject the null hypothesis. Now, a large p-value doesn't mean that we have proven that the null hypothesis is true. We simply don't have enough evidence to reject the null hypothesis. This table is a general guideline for reporting the strength of evidence against the null hypothesis based on the p-value. However, this may not be very helpful when it comes to making decisions. So how exactly do we calculate this p-value? Well, first, it will depend on the type of test that we are performing, as well as the sampling distribution model. For proportions, we know that the sampling distribution will be normal under certain assumptions and conditions, and so we will use the normal model to find the p-value. And so if we have a lower tail test, meaning that the alternative hypothesis is p is less than p naught, then the p-value is going to be the area in the left tail to the test statistic. If we have an upper tail test, this is where the alternative is p is larger than p naught, then the p-value is going to be the upper tail area to our test statistic. And if we have a two-tailed test, meaning that the alternative is p does not equal p naught, then the p-value will be the area of both tails to the test statistic. So once we have calculated the p-value, how do we decide whether to reject the null hypothesis? In other words, how unlikely does the probability need to be in order for us to reject the null hypothesis? Well, we can define a threshold called the alpha level or the significance level. And if the p-value is equal or below this threshold alpha, then we will reject the null hypothesis. And we call these results statistically significant. Now, this doesn't mean that there is practical significance. It just means that the p-value we have obtained is smaller than the specified alpha level. And some common alpha levels are 0.1, 0.05, and 0.01. Now, the alpha level is chosen appropriately for the given situation. For example, if we want to assess the safety of airbags, then we want a low alpha level. So something like 0.01 or smaller. Or if we simply want to know whether people prefer pizza with or with pineapple, then you might be fine with an alpha level of 0.1. Now we must choose the alpha level before we look at the data. Otherwise, we can manipulate our significance level to suit the data and then make any conclusion that we desire. Now, if the p-value is greater than alpha, then we will fail to reject the null hypothesis. And we should not accept the null hypothesis as we have not proven that the null hypothesis is true. The most that we can say is that the null hypothesis doesn't appear to be false, and so we have insufficient evidence for the alternative hypothesis. So this will conclude our introduction to hypothesis testing. In the next video, we will look at a structured path for hypothesis testing with a few examples, and I'll see you then.